All right, we are live. Hey everyone, thank you so much for joining me today for the Hoodie Community Sing. And if you're new here, the Community Sing allows community users and developers to meet, interact, and exchange ideas on Apache Hoodie, how it is implemented. Um, Before we get started, I'm going to give a couple minutes for people to join in. I see a couple of people already joining in. So yeah, just a couple minutes, and then we'll get started with our usual route. Let us know where you're joining in from. And if you are already in implementing Hoodie at your organization, how are you doing it? Or if you're interested with lake houses in general with Hoodie, let us know about that as well. Feel free to post it on our LinkedIn. So this session will be live, of course, but we'll take some question answers as well in the end. But again, for people who cannot make it and have registered, this will be uploaded as a recording to YouTube as well, and will be available on LinkedIn to check it out. So you can take it at your own pace, and bring out any questions that you might have. Even post it out on our YouTube channel, and we'll take it from all those places and help you get those answers. All right, just a moment. All right, I think we are good to get started at this point. So yeah, today we have yet another interesting presentation, and it's from Southwest Airlines, Southwest Data Platform team. Of course, if you're in North America, you know what Southwest Airline does. And during this presentation, our speaker, whom I will introduce in a moment, will help us get an inside look at what's happening with Southwest Airlines data infrastructure, their journey on from log legacy system to a modern high performance framework that is being powered by Apache Hudi. And the presentation will break down some of the key performance challenges during this journey, share some real world insights that could be critical for your use cases, and highlight the significant gains achieved through this transition. So, before we get into the talk itself, let me walk you through some of the community updates that since we last met. So, in the last month, we have had around 96 PRs, and that means a lot has been brewing on the Hoodie project side. We have had like 49 developers who contributed to these different PRs from different organizations, so really good diversity in there. We also closed around 9 issues, and new PRs are being worked on at this point of time. So, in general, there is some solid momentum going on there with some new capabilities, new release updates, and be sure to follow that along. I also wanted to double click a little bit on the community diversity. This is something that we usually don't, discuss in a more generic way. But on the left hand side, you can see there is a PR creator chart. That means, that's the number of pull requests that are being created in the community project and the Hoodie project. And on the right hand side, there are the issue creator charts. So you can see the number of issues that are being created. So one interesting to do, see each of this bubble that you see here are, of course, like different companies, different organizations that are getting involved together for the project. So there are different organizations who are building this community together, making the project more like solid in terms of features and capabilities. Some common names, Tencent, Alibaba, Uber, of course, Amazon, Open One House. So there are a couple of names, and it's really good to see the diversity being part of this entire project. In terms of some numbers, we have over 4,700 users now on Slack. Slack is a great place for the Hoodie users to bring up any discussions, issues while implementing Hoodie. There are some PMCs to help you chat with them. I'll share the link in the next slide for you to join. There is a QR code that you can use. On the GitHub side, we have like 5,700 stars, so really good momentum. So this is the QR code that you can scan, be a part of the community, and that way we will be more connected in a way with the project. If you also haven't followed on LinkedIn and Twitter, be sure to follow them. We post all the recent updates and all that's happening in the Hoodie project overall with the community in those social channels. So it would be really good to be connected. So with that, let's welcome our speaker, Koti Darla. Uh, Koti, welcome to the Hoodie Community Sync. Thank you so much for joining us today. Uh, I will let you introduce yourself before I do that for you. But Koti is a star, is a tech lead data engineer at Southwest. And Koti, feel free to like take it from here, and we'll take the Q&A towards the end.
Thanks, Dipankar. Hello, everyone. This is Koti Darla. I'm the tech lead data engineer in Southwest Airlines. So I'm super excited to talk about modernizing data infrastructure at Southwest Airlines using Apache Hudi. Here is the agenda for today. So we'll walk through the old architecture and then new architecture with Apache Hudi, and we see use case, how we implemented Hudi end to end, and what are the challenges that we faced, how we resolved, and the major gains. And also we look at next steps and areas to explore, and then we take questions at the end. So here is the old architecture. So we have source applications like SWA, internal applications, third-party applications, and mobile applications where we get the source data. And we use Ab initio as an ETL tool to transform the data, standardize, validate, and cleanse the data, and apply all the business logics and change data captures and use the window functions, any business logics, and then transform the data and load it into on-premise data warehouse. And so once the data loads onto the on-premise data warehouse, Tableau and Alteryx, the customers connects through them to the on-premise data warehouse, and extracts the business insights and reports from uh, the data warehouse. And moving to the new architecture using Apache Hudi. So we have the streaming and batch applications, SWA internal applications, as we already saw in the previous slide. So we have SWA internal applications, third-party applications, and mobile applications. So we get all kind of formats of data. So we have the ingestion layer where if we get the files, then we use SFTP, and if it is Kafka, then we use S3 sync connectors, and this ingestion layer loads the data into a landing zone. And once the data lands onto the landing zone, we have the data processing pipelines built to validate, clean, and standardize the data. And the clean data will be stored in the clean zone on S3. And then once the data lands onto the clean zone, then we have another set of data processing pipelines to transform the data and enrich the data model. And then we load the data into curated zone. That's where we create Hudi tables. So we use Amazon EMR for creating these data pipelines, and also use AWS Glue. So basically we use PySpark, and we have like we use step functions for orchestration. So for data management, we use AWS Glue catalog, and for searching Athena. And once the data loads onto the Hudi tables, we also load the data into the Redshift data warehouse, and customers connects to the Redshift data warehouse from Alteryx and Tableau, and they will extract the business insights and reports out of it. And also our data science teams and all, they would run data models on the data on Hudi as well. So with that, moving to the use case. So whenever the customer books a flight, so we get a reservation event in an XML format. And so it is of 20 to 25 nested levels of a very huge XML. And we our data modelers modeled this data. So in third normal form, around 30 plus tables need to be loaded, translating this XML into around 30 plus tables. And all those, most of those tables are SCD type 2. So we need historical tracking. I will go through SCD type 2 in the next slides, very high level. And very few are just insert only. So moving to the next, for those who don't know SCD type 2, I just wanted to give a very high level. So here it's a method of handling slowly changing dimensions in data warehousing. So we have, if you look at SCD type 1, it maintains only the current state. So if we take Dallas to Seattle, the price is 150. This is just an example. And if the price change from 150 to some other price, right, so 200, if you just query this table, you will see only 200, and we don't have any clue when the price changed from 150 to 200. So it overwrites the old data with new data, and we can see only the current state. So coming to SCD type 2, it maintains a full history, like when the price changed from 150 to 200. So it creates a new record for every change. So if you see here, right, so Dallas to Seattle, $150 from March 15th to here. If you just look at before 200 price, you can see this is the current record. Once the price changed, we will have the current record and then the previous record, right? So the price changed from 150 to 200. So the price 150 is from March 15th to March 18th. On March 18th, the price changed to 200. This is the current record. That's how we need to the SCD type 2 works. And we need to build SCD type 2 using Hudi. And with that, we didn't see any implementation with SCD type 2 on using Hudi. So but we found a blog from AWS saying build slowly changing dimensions type 2 with Apache Spark, Hudi, and EMR. So that's where this is the starter for us. And we looked at the blog and looked at key insights, right? So it is talking about utilizing the Apache Hudi offset capabilities to handle insert or update logic seamlessly for efficient data management. And also it's talking about copy on write or merge and read tables for faster queries. This paper mostly implemented copy on write, and also proposing to use the EMR for auto scaling and cost efficiency and high availability. We took insights from this, and we implemented for the data ingestion, we used Apache Spark and EMR, and also for change detection, deduplication, we use pre-combined logic, and also for SCD type 2s, as we already discussed before. So it insert new records for changes and maintain old records with effective start and end dates. And also we use the is current and effective end dates to identify the latest records. So with that, then we were looking at the which table format we need to use, whether it's a copy and write or match and read. That's when we dig little deeper on that, and looked at our requirement is of more of batch processing, and we need to access the previous previous batch loaded records. And as SCD type 2 needs to edit the previous loaded records based on the changes. So here COW provides faster and consistent queries for current data, and also COW reduces query overhead compared to merge and read. We don't need to read the extra logging, and which we don't want, because we are looking for the batch processing mostly, and COW is ideal for batch updates common in SCD type 2 workflows, and also it enhances data reliability and consistency during bulk operations. So we and also we consider the atomic upsets part. So COW ensures atomic updates by overwriting entire data files. So it as it overwrites the base files. So we were looking at COW, and also it simplifies the tracking of historical records with the clear versioning. Then the efficient data versioning perspective, we feel like COW perfectly aligns with SCD type 2 needs by maintaining full versions of records. And we have some out of order cases and all as well. So we have to reprocess everything. So we choose COW as in table format. So coming to use case, right? We have a couple of requirements to process our data. Whenever the customer books a flight, we get events, right? So whenever we get an events, we will right now we are loading every 2 hours, and every 2 hours batch files needs to be loaded at one go to all the 30 R tables. So if any failure in between, we have to make sure that we run that table, load everything, and move to the next batch. So we have to go with a customized DynamoDB approach, which is very helpful for us in many cases. All right. So if we are running a batch, then what we do is we use glue table, curated tables, and we use glue bookmark. And we create a batch file, and we make sure that batch file is tracked in a job stream table in the DynamoDB. So that we will make sure, okay, file one, this job loaded in all tables or not, we can look at it. So, and we have one more table uh, to check the status as well for each table, right? So suppose if you take 001 as a batch, table 1 and table 2 is complete, and 002 job with file 2 as a batch file. If it fails, right, so we have to rerun the job and make sure restart from the failure only, instead of running from again from all the tables related logics. So for that, we used step functions as an orchestration tool, and that time we didn't have the retry from failure option. So we this table design helped us a lot. If there is any failure, and if you see any completed status, we skip the completed status tables, and we only take failed status and rerun the table job. And one more requirement is we also need to load data into Redshift as well. So we have one more DynamoDB table, which tracks what is the last Hudi timeline that we extracted or loaded into Redshift. From that point onwards, we will again load the data, only delta data based on this table. So this design helped us a lot, mainly to maintain the referential integrity, and also restart capabilities from where it failed, and also for monitoring purpose and maintenance, right? So what job is running and what table is running right now, and all that monitoring dashboards are built on top of this, and which helped us to track everything. With that, yeah, so in our script, right, so we have a lot of data processing units, and we have to do, as we are getting XML with 2025 levels of nested, so we have to flatten XMLs. And also we have table scans and aggregation functions need to be used, wherein if PNR is booked, and we need to count the passenger counts, and we use sum and count and all window functions, like if we, to go to the previous records, we use lag, lead, and all window functions. Also we have to we also do multiple joins. So out of 30 tables, some tables have a dependency on the other tables, and we have to join with all those tables. And also we have the reference tables as well, which needs to be joined here. So we have the complex logic. All the business rules needs to be incorporated here, and there are self joins as well, and there is a case of late arriving data as well. I will discuss more on this in the later slides. So we have all typical uh, kind of data processing components. Um, so our process is very complex because we are applying all the business logics and SCD type 2s and all. So it's we built common utils for all the XML flattenings. So we need to flatten the 20 to 25 levels of XML into 30 plus odd tables. So what we did is we created common utils for XML flattening, and also we need to enforce the schema. And we once the data loads onto Hudi, we need to take the data to Redshift as well. And as I mentioned, window functions and aggregation functions and multiple joins. Also, we need to do SCD type 2s. So expiring the previous record and creating the current records. A lot of complexities involved in this, and And also we are using DynamoDB, so we need to see what is the status of the table on the DynamoDB by reading the DynamoDB table, and then based on that we make a decision whether to run or skip if there are any failures. So and also we have the Hudi upsend and delete logics as well. So overall it made the script very complex. So moving to the next slide. So as I was talking, right, so we get out of order data as well. So we have to make sure, right, so if we have PNR with three changes, version 1 to 3, and let's assume version 1 has price of 100 and version 2 has price of 200, and version 3 has update of price of 300 though. So if we get version 1 and version 3 first, and in the later batches if you get version 2, so historical tracking would be incorrect if you process in sequence. So we have to make sure we get everything together, and make sure we calculate the right effective start and end dates. So that's the reason what we do is so we get all the delta for that batch, and we collect all the keys and go back to the target and get all the data in from the target. And so if it is a new version, then we just reprocess and use the transformations, apply transformations. If it is already old and transformed, we use the same transformed data. And what we do is we apply all the transformations again for calculating the effective start date and end dates. So that's how. So once we get the merged data, final data set, then we use the bloom index, and using Hudi upset capabilities, we insert and update records. We also have deletes. So when we are doing this out of order case, we first time if versions comes in and out of order, what we do is we calculated the effective start date and end dates, and later if we get everything in an order, that's where we recalculate, and we found some orphan records, so we had to apply deletes as well. That's how we handled out of order data. So with all these complexities, we see a lot of performance related issues, and the job ran very slow, and we found the job taking too much time. So these are the challenges basically, right? So I'll go through the challenges what we faced. So for the XML flatten, as I already mentioned, we have huge XML with nested levels, and explode generating huge data. So with that, it's generating huge high shuffle overhead, and with that we also see some data skew, some partitions processing billions of records, and also by default 120 is the SQL shuffle partition, and for that we see memory pressure and executor failures and job failed. And then we also see executor lost due to high shuffle read and write. So if you see on the right side, I'm not sure whether it's visible or not, but here we also looked at the Spark UI, and how the explode is exponentially generating the records. So around 11 billion records generated, and even shuffle read and writes, it's in TBs, 2.2 TB and 5.1 TB. So our aim was to load, generally we load every 2 hours, but if there is a situation where we need to reprocess the last 10 days or last week, we wanted to test all those cases. That's why we took the huge data, and That's when we see all the shuffle overheads. So how we optimize this is, again, we try to use repartition and coalesce, and we try to do the balancing the distribution, and also we reduce the max partition bytes, which helped us a lot. To change that to smaller shuffle blocks. For that, we tried 16, 8 MB, something like that, and it worked very well with the huge data set. And sometimes even repartition and coalesce didn't work for us for some of the tables, big tables, and we had to go with salting techniques as well to fix the skew and straggler toss. And also we enabled adaptive query engine for auto adjusting shuffle partitions for some of the tables. So we all the tables are orchestrated in the step functions. So everything needs to be completed in one run. So we took different approaches for the different tables based on the volume of data it needs to process, and based on the business logics. So overall, we see efficiency gains here, 40 to 60% faster execution. So initially, the job used to take 5 hours or so, and later it came down to 1.5 hour. And it reduced shuffle overhead with all these optimizations, and improved memory efficiency. As we all know, it is a tedious task to look at the performance from the Spark UI and looking at the ganglia charts. And so we were able to optimize the code, and we were able to see the efficiency gains. Coming to the another challenge, as I mentioned, right, we have complex transformations. Huge business logics need to be implemented, and along with XML flattens, and we see huge DAG. So the challenge that we see is, because it needs to track too many transformation, execution is slowing down because of the long lineage complexity. And we also see a high shuffle overhead with all window functions and different business logics that we used. So multiple stages cause the large data exchanges, and because it's a huge DAG and long lineage complexity, so we see executors ran out of memory as well. And even if we see executor ran out of memory, and we see cache stages get lost and forcing re-execution, it again slowed down the performance. So these are the things that we applied from the optimizations perspective. So our aim is to break the DAG. So as we have the huge DAG and long lineage complexity, we want to avoid that, and that's when we try to use the persist and checkpoint. Even sometimes persist also fail with memory, ran out of memory issues, and then the main thing that worked for us is local file reads and writes. It helped us. I know there will be IO overhead, but still it worked very well for us to break the DAG. And So we also used repartition before explode, and joins and aggregation wherever looking at the Spark UI, and we were able to figure out a way to use the repartition, where to apply the sorting techniques and coalesce, and based on that we were able to optimize, and again adaptive query enabling. And also for the smaller data set, to avoid the large shuffle giants, we used broadcast giants as well. And wherever there is a possibility, we try to reduce the transformation complexity, fine tune the code, and drop some of the unused columns which are not needed. And we were looking at all the options of fine tuning code as well. So with all this, we were able to break down the DAG to smaller DAG, and we see 40 to 60% faster execution, and reduce the shuffle overhead, and also improve the memory efficiency. So our DAG was very heavy initially, so I took just a picture from web, but this is not the actual one. I couldn't fit ours here. And moving to the next challenge. So we initially thought of loading 10 years of history. So we have the on-premise data warehouse, and we wanted to load 10 years of data into Hudi. So job ran for too long, processing 10 years of data, because our goal is to have partition at date level. If we could take it to month or year level, we could have done it faster, but our aim is to focus more on the incremental jobs perspective. And for that, um, we we have to go with a date partition level. And for running 10 years, we see increased cost without proportional performance gains. And also, with the date partition, the main issue is for 10 years to creating those many prefixes in S3. Most of the times it was stuck there itself in creating all those partition folders. And also Bloom index like did not work for us for the 10 years, because the main reason was not on the partition, but it is on the record key. So when we are using Bloom index, we have to make sure that either we prefix with the date time or random number or something. So we applied the optimizations like that. So here we reduced from 10 years to 3 years. That is what business requirement is mainly. Initially we thought of 10 years, but with all these excessive run times, we looked at, revisited again the need for keeping 10 years, and came down to 3 years. So that's where we see like max to max, if any updates on the bookings, then that goes to generally it goes to 1.5 year, but we, to be on safer side, we kept 3 years. This cut processing time very significantly. And also we were able to retain the month day level partition. So that helped us to speed up our incremental processing. And also, as I mentioned, right, so we also tuned record key, prefixing with date time and then key. So also tuned Bloom index for the incrementals for efficiency. So overall we see shorter job execution, reduced cluster cost, because we were reducing to 3 years, and all these tunings, we were able to reduce cluster cost as well. And so it improved the incremental processing as well. um, so moving to the next one, here the biggest challenge is on the EMR cost. So we see a lot of cost spikes on the EMR side. We have high EMR cost, and because we are over provisioning clusters, and that led to unnecessary expenses. We looked at the Ganglia charts and CloudWatch monitoring dashboards and all, and it's so we observe that it's over provisioning, and also long job run times, right? It's inefficient Spark configuration, as we all know. So there are a lot of configurations that we can set up to fine tune further. So initially there were it's a trial and error initially, and then we were able to fine tune that later to our desired SLAs. And incorrect instance family as well, so mismatched with compute and memory requirements, wherein whether we need to use the compute family or memory family like C family or R family from the AWS EC2s. So that incorrect instance family selection and also uncontrolled auto scaling added nodes during peak, but didn't scale down efficiently because of fluctuating workloads. So with this, what we did is, from the optimization perspective, we switched to graviton instances, that is 20% lower cost. So we went with graviton instances, so that lowered our cost and also better performance per our dollar. We observed lower cost there after using the graviton instances. And so coming to the instance family or instance fleet, we were able to balance by looking at all the parameters and metrics. We were able to balance the compute versus memory and needs, and we made sure to have right balanced instance types. And we disabled auto scaling. This is mainly like we started with auto scaling initially, and whenever there is a fluctuating workloads, if it is idle, then all the instances are getting terminated, and whenever it sees again the workload, then it's bringing up them. That's where we see a lot of terminations and initializing instances that again it increased our costs. So thought of trying the disabling auto scaling and went with the managed scaling option, and that helped us a lot to cut down the cost. And also for the Spark configurations, we kind of fine tuned the executor memory and driver memory and partitions, and also shuffle settings, and all different kinds of configuration parameters we tried. And also when we submit a couple of Spark jobs in a cluster, there is a resource contention, and which one job is taking all the resources and other job is kind of idle. Even it shows running, but we see that it's not really having any task. So for fine tuning that, in the cluster creation itself, we added the memory fragments, and we gave the min and max settings there, and it helped us to resolve that memory contention between the Spark jobs in a single cluster. And also we used mostly shifted to using Spot instances with Graviton, and it helped us to reduce the cost without impacting our stability. And we are running as a batch jobs, and we were able to use the Spot instances and Graviton instances. And coming to the partitioning side, it is also very important. So initially we thought of going with date, and then still we went with the date, but it's based on the functionality of data. All right, so we went with a PNR date. So for the PNR, for the date, whatever the bookings happened, we want to put together everything, so that it will be easy to process. If there is any out of order cases, or if there is any new versions came in, we can only read the latest data. So that's how it helped us lower the EMR cost, and we were able to optimize the resource utilization, improve job performance. So we were able to meet the SLAs, and we were able to reduce the cost. And so this is how we were able to optimize our jobs. Um, So these are the next steps that we are thinking. We want to explore more on the Hoodie side, where we want to try merge and read. I know we were looking at batch processing, but we want to see if there is a scope to improve the upset, faster writes, and efficient upset, and for the better performance for incremental loads, and also looking at record level indexes as well. If we can we can utilize for update efficiency, and planning to also upgrade Hoodie to Hoodie 1.0. Also looking at using the secondary indexes capabilities, new capabilities that are being released as part of Hoodie 1.0. I think with that, I am done. If you have any questions, we can take.
Awesome. Thank you so much, Cody. Yeah, it was a really insightful presentation. I felt like the challenges and everything was like really highlighted well, and I think how it led to like the solution in a way, and what you had to do in that process. I think this will be really valuable for people who are looking at implementing Hoodie for this kind of use cases. And I have a couple of questions here, and I'll assume like there might be more questions as we take this. So one of the first question I have is, let me pull it up. It says from Samuel, if you can mention how Hoodie indexing are helping you, especially if you're using. I know you mentioned about secondary indexes in the future from 1.0, but yeah, I think it's in general about like indexes and what kind of indexes are you using and if they have been helpful. It would be great to know.
Oh yeah, so we are using Bloom Index, right? So initially we started at we didn't much look at record key field, right? So it didn't work out. Lookups took longer time, and upsets took longer time, and then we were looking at how we can resolve this, and we found that we're reading all the documentation. We found we need to use in a like sequence a random, or maybe appending with the timestamp, and prefixing with the timestamp will help Bloom Index to look for either first half or second half,
Yeah,
something, right? So that's how we used Bloom Index. But second indexes we are planning to explore in future.
got it.
We tried record level index as well, but I think it didn't work out. Maybe we need to look at further.
Got it. Yeah, I think there is a dependency. I think dependency is not maybe the right term, but I think the secondary indexes would be something to like look forward to. I guess we do have seen some really good results in a way. Again, depends on use cases and stuff, but that was with like the TPCDS data set. But yeah, something to look forward to, I guess. All right. So the next question is around your out of order events, and the question is maybe more generic. Is like, did you use like the Hoodie record mergers, like the event time ordering or something by default, or was it more of a custom logic that you kind of had developed for your particular use case to handle the out of order events?
Yeah, so we used our custom logic because we have to go back to the previous record, and then we need to end date them, right? So we have to expire the previous records,
Mhm.
and that's when we didn't go with any Hoodie merge or anything there. So we have to go back to previous record and collect all of those records together
I
and
see.
recalculate all the effective dates. And there are so many other logics as well.
Yeah,
When we are getting XML, right? So if one table doesn't have any updates, we have to make sure that we fill the gap between those
got
updates. The table which has updates, the table which doesn't have updates, we have to make sure, and then based on that we have to fill the gap. So that's where we went with the custom logic.
Got it. Yeah, I think that flexibility is good to have. I think Hoodie by default comes with like event time ordering and like commit time ordering. So basically, these are the two different mode by default. But of course, the ability to do something like custom is something really useful for organizations for different use cases. Uh,
And we have already the code,
okay.
so right from the legacy systems,
Yeah.
right? We
Yeah.
kind of use that. And
Exactly. Yeah. Perfect. Awesome. Thank you for that. The next question is around, I think it's around like you mentioned something around like, okay, so S3 listing probably. That's what I kind of see. So the question is around, like, you talked a little bit about how you had to deal with a lot of prefixes in S3, and that maybe there maybe there's some expensive listing and stuff. So did you leverage like the Hudi metadata table was enabled, or did you use the kind of the file statistics indexes as part of that?
Yeah, so our aim is to upset all 10 years worth of data, right? When we started, we didn't use any other Hoodie capabilities there. We tried just upset there, and there it tried to create prefixes, and it created for 3 years or 4 years, and there somewhere it stopped there and start creating more.
Yeah,
Um, yeah, that's where, okay, we were looking for the options, and also we were thinking maybe we could have tried different options, but the main thing is we were looking at majorly on the incremental jobs, right? So that's the reason we wanted to reduce the number of years to keep, so that that will help us not to scan entire tables in future for out of orders or anything.
makes sense. Perfect. Thank you so much for that. Um, I have one question, and then I'll take something else from the community. But one question from my side would be, like, you were talking about a little bit about like how you're thinking about merge on read use cases as well. Are you like thinking about more of low latency writes, or maybe some streaming based use cases at this point of time or in the future?
Yeah, so we are right now meeting our SLAs, but I see it's taking a little bit longer during upsets for COW, right? So if there is an advantage, and if it fits, MOR fits into our use case, maybe we wanted to try and speed up the upsets
Okay,
time.
makes sense. Yeah. All right. Let me see if there is anything else. Somal says we use step functions as well, and I love it. Okay, that's good. One question is, how do you efficiently implement SCD Type 2 in a NoSQL database like DynamoDB, given its lack of ACID transaction across multiple record? I don't know if this is more generic, but I think your implementation was definitely on Hoodie, as far as I saw with the AWS blog, right?
Yeah, so we are using Hudi for a CD type implementation,
Got
but
it.
DynamoDB is just for job tracking and all, right?
Yeah,
So we didn't have the read drive from failure functionality that time and step functions. That's where we wanted to find out a way not to process everything, all the tables again, whatever is complete, right? We have to process from the failure point. That's where we used DynamoDB just to track, and it is kind of um, tracking purpose and processing orchestration perspective.
got it. Got So I actually linked the blog as well. I think it's a good one to like for the community to see as well. But I think this is something you might want to look into. Like, I think this is a really good example of how you can do something in Hoodie in a Lakehouse native table format using something like Spark on EMR. Um, I think that is all. Maybe one question from me is, like, with 1.0, like if you're thinking around those lines, I think there are a bunch of new features that it kind of brings along. Also, like with the new timeline, with Swami also mentioned, like the support for LSM3 timeline now, which kind of balances the metadata, because the metadata can really grow, right, with the number of writes and stuff. So I think what makes kind of the excitement around like the 1.0, like, are you looking at specific features around that, and kind of what you're thinking in those lines?
Oh yeah, so we are looking to explore right now, right? Secondary indexes and
Yeah,
all, how we can speed up our jobs further and further. If you fine tune your jobs, you will reduce the cost, right? EMR cost. So all that perspective we are looking, but yeah, we need to go through
yeah,
full documentation, understand more capabilities from that.
awesome, awesome. All right, I think we are at kind of the top of the hour here. If there are any questions, Koti, I will gather them. I'll make sure our viewers get to them, and I'll collect everything from you. Uh, really appreciate all the time, and putting the effort, like in bringing this kind of scenario that you have already implemented within Southwest, which is really amazing to see. I think the community will be really beneficial out of this. So thank you so much for your time today. And yeah, I'll let you go and have a good one.
Yeah, we have other use cases as well, but this is the one SCD type 2 is the one.
Yes.
It's very complex one with the hoodie, right? So how we
Right.
implemented is what I wanted to show
Awesome.
here. But thanks for having me here.
Thank you so much, Koti. Yeah. All right. For everyone, bye. We'll see you on the next one.